Environmental remediation, Wikipedia audio. Environmental remediation deals with the removal of pollution or contaminants from environmental media such as soil, groundwater, sediment, or surface water. This would mean that once requested by the government or a land remediation authority, immediate action should be taken as this can impact negatively on human health and the environment. Remedial action is generally subject to an array of regulatory requirements, and also can be based on assessments of human health and ecological risks where no legislated standards exist or where standards are advisory. To help with environmental remediation, one can get environmental remediation services. These services help eliminate radiation sources in order to help protect the environment. Remediation standards. In the United States, the most comprehensive set of preliminary remediation goals is from the Environmental Protection Agency Region 9. A set of standards used in Europe exists and is often called the Dutch standards. The European Union is rapidly moving towards Europe-wide standards, although most of the industrialized nations in Europe have their own standards at present. In Canada, most standards for remediation are set by the provinces individually, but the Canadian Council of Ministers of the Environment provides guidance at a federal level in the form of the Canadian Environmental Quality Guidelines and the Canada-wide Standards Canada-wide Standard for Petroleum Hydrocarbons in Soil. Once a site is suspected of being contaminated, there is a need to assess the contamination. Often the assessment begins with preparation of a Phase I environmental site assessment. The historical use of the site and the materials used and produced on site will guide the assessment strategy and type of sampling and chemical analysis to be done. Often nearby sites owned by the same company or which are nearby and have been reclaimed, leveled, or filled are also contaminated even where the current land use seems innocuous. For example, a car park may have been leveled by using contaminated waste in the fill. Also important is to consider off-site contamination of nearby sites, often through decades of emissions to soil, groundwater, and air. Sealing dust, topsoil, surface, and groundwater of nearby properties should also be tested, both before and after any remediation. This is a controversial step as stabilization involves the addition of reagents to a contaminated material to produce more chemically stable constituents, and solidification involves the addition of reagents to a contaminated material to impart physical/dimensional stability to contain contaminants in a solid product and reduce access by external agents. Often corporations which do voluntary testing of their sites are protected from the reports to environmental agencies becoming public under Freedom of Information Acts. However, a Freedom of Information inquiry will often produce other documents that are not protected or will produce references to the reports. In the US, there has been a mechanism for taxing polluting industries to form a superfund to remediate abandoned sites, or to litigate to force corporations to remediate their contaminated sites. Other countries have other mechanisms, and commonly sites are rezoned to higher uses such as high-density housing, to give the land a higher value so that after deducting cleanup costs there is still an incentive for a developer to purchase the land, clean it up, redevelop it and sell it on, often as apartments. There are several tools for mapping these sites and which allow the user to view additional information. One such tool is ToxMap, a geographic information system from the Division of Specialized Information Services of the United States National Library of Medicine that uses maps of the United States to help users visually explore data from the United States Environmental Protection Agency's Superfund and Toxics Release Inventory programs. Remediation technologies are many and varied but can generally be categorized into ex situ and in situ methods. Ex situ methods involve excavation of affected soils and subsequent treatment at the surface, as well as extraction of contaminated groundwater and treatment at the surface. In situ methods seek to treat the contamination without removing the soils or groundwater. Various technologies have been developed for remediation of oil-contaminated soils/sediments. Traditional remediation approaches consist of soil excavation and disposal to landfill and groundwater pump and treat. In situ technologies include but are not limited to solidification and stabilization, soil vapor extraction, permeable reactive barriers, monitored natural attenuation, bioremediation, phytoremediation, chemical oxidation, steam-enhanced extraction, and in situ thermal desorption, and have been used extensively in the USA. The relatively low cost and widespread use of disposal to landfill, the lack of authoritative technical guidance on S/S, uncertainty over the durability and rate of contaminant release from S/S treated material, experiences of past poor practice in the application of cement stabilization processes used in waste disposal in the 1980s and 1990s, and residual liability associated with immobilized contaminants remaining on site, rather than their removal or destruction. Thermal desorption is a technology for soil remediation. During the process, a desorber volatilizes the contaminants to separate them from especially soil or sludge. After that, the contaminants can either be collected or destroyed in an off-gas treatment system. Excavation processes can be as simple as hauling the contaminated soil to a regulated landfill, but can also involve aerating the excavated material in the case of volatile organic compounds. Recent advancements in bioaugmentation and biostimulation of the excavated material have also proven to be able to remediate semi-volatile organic compounds on site. If the contamination affects a river or bay bottom, then dredging of bay mud or other silted clays containing contaminants may be conducted. Recently, ex situ chemical oxidation has also been utilized in the remediation of contaminated soil. This process involves the excavation of the contaminated area into large bermed areas where they are treated using chemical oxidation methods. Site assessment, also known as solubilization and recovery, the surfactant-enhanced aquifer remediation process involves the injection of hydrocarbon mitigation agents or specialty surfactants into the subsurface to enhance desorption and recovery of bound-up otherwise recalcitrant non-aqueous phase liquid. In geologic formations that allow delivery of hydrocarbon mitigation agents or specialty surfactants, this approach provides a cost-effective and permanent solution to sites that have been previously unsuccessful utilizing other remedial approaches. This technology is also successful when utilized as the initial step in a multifaceted remedial approach utilizing SEER, then in situ oxidation, bioremediation enhancement, or soil vapor extraction. Pump and treat involves pumping out contaminated groundwater with the use of a submersible or vacuum pump, and allowing the extracted groundwater to be purified by slowly proceeding through a series of vessels that contain materials designed to adsorb the contaminants from the groundwater. For petroleum-contaminated sites, this material is usually activated carbon in granular form. Chemical reagents such as flocculants followed by sand filters may also be used to decrease the contamination of groundwater. Air stripping is a method that can be effective for volatile pollutants such as BTEX compounds found in gasoline. For most biodegradable materials like BTEX, MTBE, and most hydrocarbons, bioreactors can be used to clean the contaminated water to non-detectable levels. With fluidized bed bioreactors it is possible to achieve very low discharge concentrations which will meet or exceed discharge requirements for most pollutants. Depending on geology and soil type, pump and treat may be a good method to quickly reduce high concentrations of pollutants. It is more difficult to reach sufficiently low concentrations to satisfy remediation standards, due to the equilibrium of absorption/desorption processes in the soil. However, pump and treat is typically not the best form of remediation. It is expensive to treat the groundwater, and typically is a very slow process to clean up a release with pump and treat. It is best suited to control the hydraulic gradient and keep a release from spreading further. Better options of in-situ treatment often include air sparge/soil vapor extraction or dual-phase extraction/multi-phase extraction. Other methods include trying to increase the dissolved oxygen content of the groundwater to support microbial degradation of the compound by direct injection of oxygen into the subsurface, or the direct injection of a slurry that slowly releases oxygen over time. Solidification and stabilization work has a reasonably good track record but also a set of serious deficiencies related to durability of solutions and potential long-term effects. In addition, CO2 emissions due to the use of cement are also becoming a major obstacle to its widespread use in solidification/stabilization projects. Stabilization/solidification is a remediation and treatment technology that relies on the reaction between a binder and soil to stop/prevent or reduce the mobility of contaminants. Funding remediation. Mapping remediation. Conventional S/S is an established remediation technology for contaminated soils and treatment technology for hazardous wastes in many countries in the world. However, the uptake of S/S technologies has been relatively modest, and a number of barriers have been identified including technologies: thermal desorption, excavation or dredging, surfactant-enhanced aquifer remediation, pump and treat. New in-situ oxidation technologies have become popular for remediation of a wide range of soil and groundwater contaminants. Remediation by chemical oxidation involves the injection of strong oxidants such as hydrogen peroxide, ozone gas, potassium permanganate, or persulfates. Oxygen gas or ambient air can also be injected to promote growth of aerobic bacteria which accelerate natural attenuation of organic contaminants. One disadvantage of this approach is the possibility of decreasing anaerobic contaminant destruction. Natural attenuation where existing conditions enhance anaerobic bacteria which normally live in the soil prefer a reducing environment. In general though, aerobic activity is much faster than anaerobic and overall destruction rates are typically greater when aerobic activity can be successfully promoted. The injection of gases into the groundwater may also cause contamination to spread faster than normal depending on the site's hydrogeology. In these cases, injections down gradient of groundwater flow may provide adequate microbial destruction of contaminants prior to exposure to surface waters or drinking water supply wells. Solidification and stabilization. Migration of metal contaminants must also be considered whenever modifying subsurface oxidation reduction potential. Certain metals are more soluble in oxidizing environments while others are more mobile in reducing environments. Soil vapor extraction is an effective remediation technology for soil. Multi-phase extraction is also an effective remediation technology when soil and groundwater are to be remediated coincidentally. SAVE and MPE utilize different technologies to treat the off-gas volatile organic compounds generated after vacuum removal of air and vapors from the subsurface and include granular activated carbon, thermal and/or catalytic oxidation and vapor condensation. Generally, carbon is used for low VOC concentration vapor streams, oxidation is used for moderate VOC concentration streams, and vapor condensation is used for high VOC concentration vapor streams. Below is a brief summary of each technology. Using nano-sized reactive agents to degrade or immobilize contaminants is termed nanoremediation. In soil or groundwater nanoremediation, nanoparticles are brought into contact with the contaminant through either in situ injection or a pump and treat process. The nanomaterials then degrade organic contaminants through redox reactions or adsorb to and immobilize metals such as lead or arsenic. In commercial settings, this technology has been dominantly applied to groundwater remediation, with research into wastewater treatment. Research is also investigating how nanoparticles may be applied to cleanup of soil and gases. Nanomaterials are highly reactive because of their high surface area per unit mass, and due to this reactivity nanomaterials may react with target contaminants at a faster rate than would larger particles. Most field applications of nanoremediation have used nano-zero-valent iron, which may be emulsified or mixed with another metal to enhance dispersion. That nanoparticles are highly reactive can mean that they rapidly clump together or react with soil particles or other material in the environment, limiting their dispersal to target contaminants. Some of the important challenges currently limiting nanoremediation technologies include identifying coatings or other formulations that increase dispersal of the nanoparticle agents to better reach target contaminants while limiting any potential toxicity to bioremediation agents, wildlife, or people. Bioremediation is a process that treats a polluted area either by altering environmental conditions to stimulate growth of microorganisms or through natural microorganism activity, resulting in the degradation of the target pollutants. Broad categories of bioremediation include biostimulation, bioaugmentation, and natural recovery. Bioremediation is either done on the contaminated site or after the removal of contaminated soils at another more controlled site. In the past, it has been difficult to turn to bioremediation as an implemented policy solution, as lack of adequate production of remediating microbes led to little options for implementation. Those that manufacture microbes for bioremediation must be approved by the EPA. However, the EPA traditionally has been more cautious about negative externalities that may or may not arise from the introduction of these species. One of their concerns is that the toxic chemicals would lead to the microbe's gene degradation, which would then be passed on to other harmful bacteria, creating more issues, if the pathogens evolve the ability to feed off of pollutants. In situ oxidation. Cleaning of oil-contaminated sediments with self-collapsing air microbubbles have been recently explored as a chemical-free technology. Air microbubbles generated in water without adding any surfactant could be used to clean oil-contaminated sediments. This technology holds promise over the use of chemicals for traditional washing of oil-contaminated sediments. In preparation for any significant remediation, there should be extensive community consultation. The proponent should both present information to and seek information from the community. The proponent needs to learn about sensitive uses like childcare, schools, hospitals, and playgrounds, as well as community concerns and interests information. Consultation should be open, on a group basis, so that each member of the community is informed about issues they may not have individually thought about. An independent chairperson acceptable to both the proponent and the community should be engaged. Minutes of meetings including questions asked and the answers to them and copies of presentations by the proponent should be available both on the internet and at a local library or community center. Soil vapor extraction. Incremental health risk is the increased risk that a receptor will face from a remediation project. The use of incremental health risk is based on carcinogenic and other effects and often involves value judgments about the acceptable projected rate of increase in cancer. In some jurisdictions this is 1 in 1 million, but in other jurisdictions the acceptable projected rate of increase is 1 in 100,000. A relatively small incremental health risk from a single project is not of much comfort if the area already has a relatively high health risk from other operations like incinerators or other emissions, or if other projects exist at the same time causing a greater cumulative risk or an unacceptably high total risk. An analogy often used by remediators is to compare the risk of the remediation on nearby residents to the risks of death through car accidents or tobacco smoking. Standards are set for the levels of dust, noise, odor, emissions to air and groundwater, and discharge to sewers or waterways of all chemicals of concern or chemicals likely to be produced during the remediation by processing of the contaminants. These are compared against both natural background levels in the area and standards for areas zoned as nearby areas are zoned and against standards used in other recent remediations. Just because the emission is emanating from an area zoned industrial does not mean that in a nearby residential area there should be permitted any exceedances of the appropriate residential standards. Nanoremediation. Bioremediation. Collapsing air microbubbles. Monitoring for compliance against each standards is critical to ensure that exceedances are detected and reported both to authorities and the local community. Enforcement is necessary to ensure that continued or significant breaches result in fines or even a jail sentence for the polluter. Penalties must be significant, as otherwise fines are treated as a normal expense of doing business. Compliance must be cheaper than to have continuous breaches. Assessment should be made of the risks of operations, transporting contaminated material, disposal of waste which may be contaminated including workers' clothes, and a formal emergency response plan should be developed. Every worker and visitor entering the site should have a safety induction personalized to their involvement with the site. The rezoning is often resisted by local communities and local government because of the adverse effects on the local amenity of the remediation and the new development. The main impacts during remediation are noise, dust, odor, and incremental health risk. Then there is the noise, dust, and traffic of developments. Then there is the impact on local traffic, schools, playing fields, and other public facilities of the often vastly increased local population. Dioxins from union carbide used in the production of now banned pesticide 2,4,5-trichlorophenoxyacetic acid and defoliant agent Orange polluted Homebush Bay. Remediation was completed in 2010, but fishing will continue to be banned for decades. An EU contract for immobilization a polluted area of 20.000 cubic meters in Baker, Croatia based on solidification/stabilization with Imosem is currently in progress. After 3 years of intensive research by the Croatian government, the EU funded the immobilization project in Baker. The area is contaminated with large amounts of TPH, Pa, and metals. For the immobilization, the contractor chose to use the mix-in-plant procedure. Community consultation and information. Incremental health risk. Emission standards. Transport and emergency safety assessment. Impacts of funding remediation. Examples of major remediation projects. Homebush Bay, New South Wales, Australia. Baker X coking plant site, Croatia. General links. Legislation about remediation. Environmental groups with information. Environmental protection agencies. 2.